So this is 7-4, which is a one-day lesson. So you understand what's happening here? We're approximating the length of the curve. So that secant line would approximate the length of the curve. It's hitting the curve twice, okay? It's going to underestimate the length of the curve. Yes, I can see that. But the shorter the length of that secant line, the more accurate it's going to be the length of the curve. So we're calling that ds, which is the change in the hypotenuse. What? It's a Pythagorean. You get a right angle here. We created this triangle. It's over there. So we take the square root of both sides, and we get the length of the curve is that. Is that logical? 100%. If you wanted to do this, if you wanted to approximate the length of the curve, then you could create this Pythagorean triangle and then solve for the hypotenuse. So now ds is a small change. Like that just has been expanded to help you see it. You think of ds as like a really small change, you want to add up all these ds's. You want to add up everything on the right. A little bit of algebra here. What did they do? You multiplied this thing by 1 in the form of this. Dx over dx is 1. So dx squared over dx squared. When you take the square root of that, because you can distribute an exponent over multiplication, that would be the same as dx over dx, which is 1. Make sense? Now what happens? We distribute this down here in the denominator over this, over that sum. So the denominator is down here, goes to there and there. The numerator of this stays there, under the root sign. You're in effect going to memorize this. It's not that complicated to memorize, but you want to see what they did. If you just multiply by 1 and distribute the denominator over this, over the fractional exponent, it would look like that for both terms in the parentheses. This is divided by itself, that's 1, plus this times that dx. Well, now I can anti-differentiate. Why? Because you took the square root of dx squared to get that dx. And again, you can distribute an exponent over multiplication. And the root sign is a fractional exponent, and we keep each term, this factor and that factor, their own square root symbol, and that would simplify to just dx. That would be the length of the curve, which is this. You find the limits. It is the square root of 1 plus y prime squared times dx. So here's an example. We want the length of this curve, which is what? It's y equals negative x squared, and it's been moved up 9. From 0 to 3. We want to know, how long is that curve if we straighten it out? The length of the curve. So the derivative of the function would be a negative 2x. We're not doing the whole derivation now. We're just using the algorithm. So we're going to anti-differentiate this thing, dx. So we're using the x values as the limits from 0 to 3. The square root of 1, again, we're not starting from the beginning. 1 plus y prime, the quantity squared. Where there's a dy dx, you just put in negative 2x. Cartesian plane is the xy axis. It's named after Descartes. As opposed to like polar graph paper. Have you ever seen polar graph paper? You haven't? I'll hand it out later. Polar graph paper just has the concentric circles. It's another way to plot points as opposed to Cartesian plane. So now what? Well, you still have to anti-differentiate this, yes? So mu is 1 plus 4x squared. And you go into the calculator. So it's a calculator question, so you're going to go here. You're going to type this in your calculator. Go to Y1, and you're going to see, did you notice, the problem we told you that we're going to go to 2011, number 1, and number 1 and 2 are calculator questions. The length of the curve. So you're going to Y1 and just type this in Y1. The square root of 1 plus 4x squared put under root sign. Second equation, math 9 y1 from 0 to 3 dx. You get some number about 9.747. You get that? Now, what is that saying to you? It's saying this. You got this picture, and if you drew this hypotenuse right here, you have 9 squared plus 3 squared equals the hypotenuse squared, and that has to be bigger than that. Does that make sense? It's got to be bigger than 9.486. If we just drew a, if we just created a right triangle there, because the shortest distance would be that hypotenuse. Okay? So let's start with this thing. See if this makes sense to you. Suppose that's the question. What do you notice about the choices? They're all what? dy. So the problems are all dy. What would you have to do? You have to rewrite what x equals in terms of y. Yes? Just like we did with volume. So the problem's done dy. Rewrite that. What would you get? You have x to the 2/3 power equals y. Raise both sides to the 3/2 power. What'd you get? You get x equals y to the 3/2. Correct. But you have to take the derivative of that. So the derivative of that would be 3/2 y to the 1/2. And when you square that, you would get 9/4 y to the 1st. You went from 0 to 1, the graph's symmetric, they want a -1 to 1, so you'd have to double that. But that's where the answer's coming from. So, right? That's what y equals. We got to find what x equals. What goes in here? The derivative squared. Here's the derivative. Then square it. Okay. This isn't that big a deal. The length of curves is not a big deal. So, back up. There was the choice A. Okay. But I mean, some of those choices kind of stand out. Like B is the only one that goes from -1 to 1, and A is the only one that doubles from 0 to 1. So if you thought it was E, well, that makes sense, but you have to take it's the derivative squared, not what x equals squared. So here's example 1. We want the length of the sine wave from 0 to 2 pi. So this is the sine wave. What are we going to do? We're going to have the square root of 1 plus the derivative of what we want, square it, dx. The derivative sign is cosine. So we're going to go from 0 to 2 pi, 1 plus cosine squared, under the root sign, anti-differentiate that, and you get 6 740 thousandths. So as long as you type what you're doing in here accurately, it's going to be a calculator question. So if you're doing the problem dx, this would be y prime squared. If you're doing the problem dy, that would be x prime squared. So I'll pause the video and send you to problem number 9. What do we have? We want the length of the secant curve. So the derivative of the secant is secant tan. You can distribute an exponent over multiplication. The only thing you got to be careful of is the way you type it in your calculator. The secant wave from -pi/3 to pi/3. You could have doubled it from 0 to pi/3. You would have been the same. The only thing you had to do there was know the derivatives of your trig functions from section 3.5. And this is not something you're going to postpone. Well, I'll wait until April to study that. Take a moment, make sure your output of the calculator agrees with that. And if it doesn't, try and troubleshoot what it is that isn't matching up. Please tell me you're not doing it. All right, so we're going to move on to example 4. So look what you have in example 4. You have this absolute value in there, and you're going from -4 to 4. And you have a cusp there. Yes, I see that. When x equals 0. So you can't anti-differentiate this thing from -4 to 4. You have to break it down into 2 parts. Yes? If the thing's not differentiable over the domain, you have to break it down to when it is. Except, this is a little presumptuous the way they wrote it here, because there's a little more work than they're letting on. How did they get these derivatives? So when x is negative, you would get, ready, x squared plus a -3x, and then you put a -x in there. So this has to be a positive output. In order to get that curve, that branch of the curve, you would have to put this in there. When x is positive, it's pretty easy. You're just doing this. When you look at the left, if you put this upper input in there, you're not going to get the same curve. And they didn't even cover that in the textbook. They just went and said, oh, you go from here to here. So what have we got? The derivatives would be 2x plus 3, 2x plus a -5. And I said, okay, let's go from -4 to 0. And then go from 0 to 4. And it ends up being the curves are the same length, which you can't anticipate. Curves are the same length. So you end up with 19 and 556 thousandths. But you need to be careful of the absolute values. That fouls me up all the time. You got it. When you do the absolute value, it's going to be a calculator question. You got an absolute value in there, draw the branch of the curve and make sure it matches what you're looking for. All right. So we'll leave that up there and ask you to go to 27. Okay, so for this problem, you've got x cubed plus a negative 5x, and then at the y-axis, it becomes x cubed plus 5x. So here are the two derivatives. What are you doing? You're adding the first one from -2 to 0, and the second one from 0 to 1. And you don't want to truncate your answer. You don't want to round it to 3 places until you're finished. So I took this and said, store this one in L, alpha L, and then just add the answer to the right to alpha L, and then truncate that. 13 and 132 thousandths. Okay? So what you had was the function was continuous, but it wasn't differentiable. So you had to break it down into 2 branches. So here's what's going to happen. For the children that are at home, before we send you the exit ticket, you have to realize what's going to happen. I'm going to continue recording, and we're going to go to that FRQ. So this will be posted to the YouTube page today. And if you want to see what the work looks like for the FRQ, you have the solution guide, and you can come and check out the tail end of this recording. Okay? So while you're going to do the exit ticket, everybody in the room is going to the FRQ. So the children at home are dismissed to do the exit ticket. All right, so here's what the answer looks like. There was 3 points. What are they saying? 1, which is starting at the point 0, 1 and going down, plus k, which is going from 0 to k. It's the length of that segment, plus e to the 2k, which is the height. What's the length of the curve? You take the derivative of e to the 2x, which would be 2 times e to the 2x. It's e to the mu. The derivative of e to the mu is e to the mu d mu. You have 2 times e to the 2x. Square that. That's under the root sign with 1 plus that from 0 to k. That whole thing is worth 3 points. Okay? So you weren't asked for a numerical answer, and that should look pretty logical, I hope.